So welcome everyone. I think it's already our fourth class. Yeah. Let's share the screen. Okay, perfect. So today we will talk about ordinary differential equations. Yeah. But before you will see it in a second. Yeah. But before we'll delve into this, do you have any questions about anything?
For one of the reports. As for the second one, I have like now 3 pages.
Could you tell me more?
I have like a question of the class maybe for one of the reports for the second one.
Okay. So the questions after the class. Sure. Yeah. Uh, so if there is no remarks about the report or no questions about this, so yeah, this is great. Yeah. I wonder. Okay. I wonder why the screen is not working, but okay, now it's fine. Yeah. So I got one or maybe more emails, send that looks like, someone sends me the code, tells that it doesn't work, and tell me what is going wrong with it. So, well, I won't reply to this kind of emails, yeah, because I can answer many questions, yeah, and if you have some certain issues, of course, yeah, but not to this level, yeah, because it's too generic, because everything can goes wrong, yeah. So, but if you have this type of issues, yeah, that you really don't know where to go, then we have to meet. Okay, make sense? Okay. So let's go. Ordinary differential equations, yeah? So the plan for the next few lectures, so now it's fourth meeting, fifth, sixth, seventh meeting, and then we have this autumn break, yeah? So it would look like that today we talk about ODEs, yeah? Hopefully next time we'll talk about solving nonlinear equations, yeah? And then the next two classes will be given by my colleague, Alexander Nemov, yeah, who will talk about PDEs. In application, I think, among others, to finite element methods. Okay, yeah. Okay, if no questions, really no questions about everything, everything's fine, assignments are good. So maybe okay, and now you are telling me this after the whole week. Yeah, because, yeah, that's true, because there was something about those fit signs, yeah? Yeah, that you sent me. Yeah. Okay, so I will change the name. Sorry about that. Yeah. I think that I cannot say which one are easier, the one that are really deal with numerical integration of those ones. Yeah, because yeah, I remember that was something like that. But also the last year, I think that I make the same mistake, and also nobody complains. So somehow it was transferred here. Yeah, but okay, I believe that many of you almost solved them. So yeah, I think that it won't be any good to change them to anything else. And maybe it's even better because some people who complain that the MATLAB programming are changing for them, and those tasks came from this I think earlier chapter that just talks about basics of programming. I will think about okay, but yeah, it's a little pity that it's not about numerical integration. So I will think about this. Okay, thanks. Maybe I will combine something with ODEs. Yeah. So then maybe it would make more sense. Yeah, make some smaller assignments that combine numerical integration and ODE. Yeah, a good point. Thanks. Anything else? Okay. Okay, ordinary differential equations. Yeah, have you ever met them? Yeah, hopefully. Yeah, they are, they form the basics for dynamics. They are one of the most common way to represent the physical phenomena. Yeah, and they are very common in physics. Yeah, in engineering. Yeah, and when we analyze any kind of the motion or development of the systems, very often we end up with them. Yeah, one of other form of differential equations. And yeah, here are some examples. Yeah, that we are dealing with then dynamical systems that has some state, because we are figuring out how the state has developed. Yeah, and there are many examples, like like in physics, the first case. Yeah, like simple pendulum, of course. Yeah, or the car, or far more sophisticated and complicated system. Yeah, that can came with like thousands or hundreds of thousands of bodies. Yeah, to model the granular, the soil. Yeah, and then there's the mechanism of Mars lander that goes there. Spreading the diseases, yeah, is another example. It's very simple. It has very simple model, and we will start with this. And of course, weather. However, I think that then they are dealing with slightly more complicated system, maybe probably some PDEs. But yeah, but in general, as you know from early physics, the rules for dynamical systems takes the form of differential equations. Yeah. About the quizzes, yeah, I also prepare for you some not so complicated quizzes for today. Not really. I think that I have just one or two questions that are really, really little tricky. Of course, here we have assistant, yeah. But yeah, yeah. Let's take a while. Yeah, invite students. Yeah. So if you haven't sent it, I think it's the same room like the last time. Yeah. So you have somewhere the session, but uh, here is the invitation for the room. And the question states, what is an ordinary differential equation? Simple like that. And some issues, should I make it larger? Okay. So for those quizzes, somehow I'll put them and just assign those 10 extra points based on your involvement in the total number of the courses, of those quizzes. Make sense? No, it's too much hassle. Okay, I'm joking. It's not too much hassle because I could have here the report, but it's kind of pilot case. I ran it the first time, and there are some glitches, yeah, and not all those questions are for sure perfect, yeah. So, however, I don't. It doesn't seem that it makes a big of the difference, because most of the answers gets 90+%, yeah. But still, okay. Let's, because it's the first one. Let's give like 20-30 seconds, and we'll continue.
languages have you used?
In the past?
Yeah,
Or overall, in general, yeah. So I have used Fortran quite a while because it was still quite popular in engineering and many procedures were written there. Yeah, I have used some C, but mostly C++. I'm not very proficient in it. It's super complicated language. Yeah. So, writing some C code like for engineering task, it's not an issue, but to write some, big project, yeah, uh, it'd still be doable, but especially with legacy code. But okay, yeah. So C++, I use some Python, I use JavaScript, I use PHP, yeah, because I was also working as a web developer for a while. So also a little of C or C, I think CSS, yeah, Cascade style sheets, yeah, and very few of HTML, but only what I needed. I work also in C Sharp, yeah, and of course MATLAB, Julia, yeah. I try to learn a little of ML language. It's not machine learning. It's just one of the, I think, Lisp variants with very strange syntactic, yeah, and and it's fully functional language, yeah. But I just get the basics of it. Yeah, so stuff like that. And maybe some smaller ones when I need them, but mostly those. Okay, but yeah. Okay. And a question involving derivatives of function with respect to multiple independent variables. Okay, so it was tricky question because it asked about ordinary differential equation, not equations. So that's why equation with derivatives of function with respect to a single independent variable. Yeah, so that's why it was tricky, I suppose. But okay. So still. Okay, let's continue. ODs. The characteristic that is the unknown in a differential equation is a function. Yeah, makes sense? Because we are looking of what happens in time, typically. Of course, it can be in any other variable, like here, y of x, yeah. But for dynamical systems and in mechanics, typically we are trying to solve and figure out what is happening in time. In case of a finite element method, we often try to figure out what happens in space. But yeah, but those are two most common scenarios, times and space, yeah? And we are looking about the distribution, so in practice, we are trying to approximate a known function. Equations usually involve the function, its derivatives, and some other terms. Pretty clear, yeah? Because it must, yeah, I think it's pretty clear. Yeah, nothing fancy here. So typically we have those two forms, yeah? Explicit form, when we can express derivative, yeah? So the derivative that is provided for us as a function of x, so our variable and our unknown function, yeah? And there is also implicit form that is typically harder to solve, and there are special algorithms for it, and we won't get there. Yeah, fortunately, most of the examples in mechanics are explicit, can be written in explicit form. Yeah, so in implicit form, we just have some function that includes in one way or another the same set. Yeah, so the variable across which we are trying to find the function itself and its derivative. Yeah, and all is equal, oh, sorry, and all this is equal to 0. We'll start with simple first order ODE. Yeah, so it should be without S. So first order ordinary differential equation. Then we'll move to oscillating mechanical systems because those are the most basic systems that we try to solve, and they already can pose some challenges. Yeah, so as you can guess, oscillating mechanical system is, mass spring damper in our case. Yeah, we can add many of them if needed. And then here are examples of some typical schemes. Yeah, do you know any of them? Hopefully you know some of them. Yeah, so one of the most basic is forward Euler method. Yeah, we'll start with it because it has very easy interpretation and it's very easy to just derive it. Euler-Kromer scheme, which will appear to be very useful in mechanical systems. Yeah. It's symplectic integrator, and of course, the whole family of the Runge-Kutta schemes. Clear? Yeah. And yeah, it's easier to make those kind of quizzes for the introduction. Yeah. So let's have here some. Yeah. Question number 2. If you still need the code. Which numerical method is commonly used to approximate solutions, I think, to ODEs? Newton's method, Euler's method, trapezoidal rule, and Simpson's rule. Do you know all those names? Which one is unknown? Okay, I can barely hear you, sorry. So, okay. Okay, so they are all, we already very briefly talk about them. And, we even write program for trapezoidal rule. It was composite trapezoidal rule, but we use it in numerical integration. Simpson's rule is the same, it's used in numerical integration. Okay, but yeah, so uh, yeah, okay. Someone mentioned Newton's method, yeah, and Euler's method get the most, and this is clearly the right answer, yeah, because also forward Euler is called just the Euler's method. Newton's method we will discuss next time, and Newton's method is one of the methods to use to solve nonlinear equations. Okay, but I can see that I should have another question. Which of the following statements about ODEs is correct? Okay, yeah, it makes sense that it's here. The unknown in an ODE is always a constant. ODEs can be written in both explicit and implicit forms. Forward Euler is the only numerical method used to solve ODEs. ODEs always represent mechanical systems.
First question. If the unknown variable is a matrix, is it still one variable or variables?
It's unknown variable, or you mean unknown?
Solve for as a matrix. It's still a variable.
Yeah, but we are looking for a function.
Yeah.
So you mean a matrix of functions? So then or vector of functions. So it's clearly multiple variables. We just represent them for convenience, and we will do this all the time. Yeah. So we'll do this all the time by representing it by convenience in as one variable. Yeah, we use standard bolded notation that you may already know to represent vector quantities. Yeah, but of course it contains multiple functions that we try to solve at once. but we start to be a little philosophical. But technically, there are many.
Like one time we used an ODE solver. We had like a matrix solver. Basically, we had two matrices which solve like another matrix. That's why I asked.
Okay.
That's why multiple people answered like the multiple variables.
Okay. But then we have all that. That's why we discuss mostly about ODEs. But it's a good point that I should replace this question. It can be misleading. That's why I also, mostly based on participants than right answers. I have to write it down. Okay, I'll write it down right after. But okay, about the results. Yeah, wow, yeah. So yeah, people are listening. Nice. We get 100%, so it's really possible. Okay, population growth. Yeah, while we do population growth, we go to this pretty quickly. Yeah, we'll do this because the form of this is very easy. It models some physical. Okay, maybe not. It's a little about the biological phenomena, but I suppose that you also know it. Yeah, I think it's pretty basics. Yeah, and it's pretty understandable and can be easily solved using forward Euler method. Yeah, so pretty good point to start. Yeah, because already forming those equations in the way that are suitable at when we have this second order differential equations. Yeah, sometimes it's challenging, but okay. Population growth, model growth of cell culture, animals, human population. I think at least I was introduced with some rabbit population, but all are similar. Yeah, and this is the most basic equation. Yeah, that doesn't take into account any resource limitation. Yeah, so it says that we have n, which is the number of individuals. Yeah, in the population at time t. Okay. So we have, for example, this 100 rabbits, yeah, at time 0. N is integer in real life, but we model is at real value. Yeah, I hope it's clear. Why? Because it's just much easier for us. Yeah, because all the solvers works with real numbers. So we'll simply somehow, round them if needed. Yeah, or just, yeah. And error, we could include it in the model, but then the model would be not so straightforward and pretty nonlinear. Error is a number, yeah, and it tells about the growth rate, yeah, so we have to get it from somewhere. It's also nice because we have a solution for this example, yeah. So the solution for this example is like here, yeah. So it's some constant value that depends on initial conditions, as always, yeah. And e to RT. CSN number, yeah, to make solutions unique, we must define it exactly using, for example, initial conditions. Exactly. First order equation, we need one condition. Yeah. And typically we work with the system when we have initial conditions, not boundary ones. So we said that at n at time 0 is equal to n0. Then nt, n of t is equal to n0 times e rt. Yeah, but by clearly checking that e to 0 is 1, so c is equal to n0. Nothing fancy, I hope. But if you have any questions, let me know. In general, model consists of differential equations and initial conditions. Yeah, this is the way how we define the problem typically, to be able to solve it numerically. Yeah, so all the solvers also go for it. Questions? Numerical solution. Yeah. There is a large collection of numerical methods for solving equations for this. Yeah, even if you go just to MATLAB, you can find like, I don't know, maybe 10 methods. Yeah, they have different uses, and there are many reasons why there are so many of them. There are many different differential equations, and they have different characteristics, and some of them needs a special method. We'll see even today. And u is a known function, as we discussed, and f is some known formula. Yeah, we have seen, for example, this formula here. Yeah, So this is the formula that is provided for us, yeah, and it's expressed as the equation, and then we have to transform this into f, typically by moving all the statements at one side, yeah, depending on the form that is required. But for the okay, no, not on the one side. It would be on the one side, sorry. It would be on the one side when we have, for example, those implicit form, yeah. But in explicit form, exactly we need it in that way, yeah. That in explicit form, we have that derivative is equal to some function, yeah. So here we have exactly this function. Okay, and f is some formula, for example, for our case, yeah, so for our case of population growth, we have just this formula, yeah, because it was written, as you recall, that n prime of t is equal to r times n prime, and not n of t, yeah, n prime is equal to r n of t, yeah. So using the general notation, we replace u n with u, yeah. So we have u prime of x equal to or y, depending on notation, r times our function, like this, like on the next slide it was u. So this is our function, r times u, simply. Yeah. So we have r times u. And as we can see, it doesn't depend explicitly on time. It depends only implicitly on time. Everything clear? And then, so this is the formulation of the problem. Yeah. So this is the form of our problem. This is how our function looks like. And then based on this, we want to find u. Knowing also that u0 is provided. Okay, so how it is solved? Firstly, we introduce a mesh in time. Yeah, so here we have problem in time or in our independent variable, but we introduce a mesh. Yeah, so we put just like that. Yeah, because we have numerical solution and those are the simple methods. And do you understand what does it mean, mesh in time? That because we will define some time step or number of the steps, and we will solve the problem from 0 to time t end, for example, 1 or whatever is the value, yeah. And then by introducing mesh, it means that we'll cut it into just intervals, time intervals, yeah. And all those points at the end of the intervals will provide us with mesh, yeah. So we'll have 0, 0 plus dt, 0 plus 2 dt, and so, yeah. So we have all those time points. And we will find the solutions only at those time points. This is the way to approximate the solution, yeah? So we are not providing explicitly what is value of the u, yeah, for numerical solutions. We are providing only the solutions at mesh times. That's why from those algorithms, you will get typically two vectors, yeah, or matrices. And one is just time with those times points, time meshes, and the second one is the values of the u. Here is just one or ODE, so only it will be the vector with the value of the u and those time points. And this is how numerical method works. Okay. And we look for the unknown u at the end, so at each time. Okay. So this is the way how we'll define this function as two numerical vectors. Clear? Assume that the differential equation is valid at the mesh points. Okay, it must be valid there. Yeah, so that one we can evaluate it. And for mechanical systems, typically it's not an issue. Approximate derivatives by finite differences. So here we take this approximation step because we cannot solve it directly. So, and those numerical methods always include some approximations, yeah. So in one way or another, we have to approximate it by using one or another form of finite differences. Okay, do you know what is finite difference? Here we have example of finite difference, yeah, on this plot. So this is approximated derivative, yeah. So and here is, by the way, here we can see the mesh points, yeah. So finite difference, yeah. It's typically the method to approximate a derivative. Okay, so you know that for a single variable here, like let's say that this is our unknown u of t, yeah. So when you have derivative, you know, it will define this tangent at this point, yeah, u prime, yeah, because value of u prime says what is the angle of this tangent, yeah, but we don't, yeah. And finite difference if the way is the way to approximate this tangent. Yeah. So we just take 2 points, 1 point, 2 point, and provide a line. Yeah. And based on those 2 points, we tell that this line is close to reasonably close to the tangent line. Okay. And then it follows, of course, the same approach that if we have the points that are distant, like in this case, yeah, this line that came from finite difference is quite far from the tangent, but as those lines will go together, we'll get the tangent. Yeah. So this is also the promise that when we make the mesh tighter, yeah, so we'll use more points, the accuracy will improve. Okay. So okay, makes sense? Yeah. So we can approximate the derivative by finite difference. Yeah, and you have seen one of the examples. It was forward in finite difference, and then we formulate algorithm to get u of n having previous values ui. Okay, so we just start. Also, that's why this method is just suited for solving those initial value problems. Yeah, so we start at 0. So we have u0, we have t0, and based on this equation, we can calculate u prime 0. Yeah, and having this, we have to go forward and calculate u1, and all at times t1. Yeah, and all this procedure is to do this forward in time. Yeah, so we calculate u1. And then based on U1, yeah, we can approximate, because then it's U1 is already approximation. We can approximate U prime 1, yeah, and we have T1, and then that way we will just go all the time forward in time. Make sense? Yeah, we will see the equation soon. And we have some quiz here. What is the general approach to numerically solving an ordinary differential equation? Solve the equation analytically using symbolic methods. Discretize the time domain and approximate the derivatives using numerical methods. Assume the solution is constant for all time steps. Use the exact solution formula for all ODEs. There should be an option to put it all times on. Okay, let's take a second and see if there is some. Okay, nothing on the chat. Okay, let's see the results. Yeah, nice. Yeah. Okay. Clear, more or less. I think that first step is pretty easy. Introduce mesh in time. Yeah. Introduce mesh in time. So we just, slice it into time. Then we assume that our function, like here, u of t, or here, u of t, is just valid for all those times. Yeah, so we require some kind of the smoothness. Yeah, and there is not the case that at some point it just doesn't exist. Yeah, because then we cannot solve it numerically in that way, at least. And then we are starting from this point. We are just merging forward in time to get it for the next points. And now we have to figure out simply what is the formula that will allow us to do this. Okay. So introduce a mesh in time uniform. We look at for the unknown u at Tn. Yeah. So Tn is simply n dt. dt is our time step. Yeah, we start at 0 typically. Yeah, it's easy to shift. So let's say that we always start with 0 in our case, up to some nt from, yeah. And at end time, we'll get just n equal to nt trials. Like 100 steps, 1,000, whatever is needed there. We already have practiced this with numerical integration, how to get those numbers. We assume that the differential equation is valid at the mesh points. Yeah, original equation is valid for all t and approximation. So yeah, simply this function that we provide f is valid. And in our case, we can see that it's clearly valid. Yeah, because it's just r times u. Nothing complicated. And then the crucial steps of approximate the derivative by using finite differences. Okay. Using derivative definition from calculus book, there are other formulas. Yeah, so this is just one of the formula to get the derivative using finite difference. Maybe you have even seen this. Yeah, on the basic calculus. Yeah, that as I remember, this is one of the definitions that to calculate u prime, you just calculate u of t plus dt minus ut over dt, and you get the exact value, assuming that at the limit for dt to going to 0. Okay. Yeah. So in this case, yeah, we have here u of t. Here we have u of t plus dt. Yeah, or written u or t n plus 1. Yeah, and as t gets smaller, this point gets closer to this blue point. Yeah, and at the limit, they will almost meet, and then we'll have defined the proper tangent. But of course, we have limited resources, so we cannot go with those super small steps. Yeah, but okay. So for the mesh points, we have u prime of tn equal to un plus 1 to un over dt. Simply we change the notation from those t plus dt to mesh points. And instead of limit, we use small dt, giving computable approximation. And this is formula for forward difference. So as you can guess, the formula for forward difference is the base for forward Euler. And this is the reason the name comes from. Yeah. And Euler comes from, as you can guess, from Euler. Okay, so here we have a forward difference method, yeah, that we can approximate this derivative at time n, having value at time n, and knowing the mesh size. Yeah, and as you can see from this formula, we can calculate un plus 1 directly after rearranging, and this is the goal. Yeah, because this is needed. This is known. Let's say, for example, at time 0, this is known. Yeah, because it's also at the same time, so we can calculate the value of the function on the next time step. So we just formulate the algorithm as the last step to get un having previous ui. Yeah, from I smaller or the n. Yeah, typically we here in forward Euler we just use the one step behind us. Yeah, but there are multi-step methods. So yeah, so simply plug in forward difference into differential equation. Yeah, and then after arrangement we get this formula. Yeah, so we can calculate un plus 1 equal to un plus dtf. And this is just forward Euler formula. Simple? I think it's very simple, at least to me, because it's just, super simple. Now having starting value u0, we can advance in time. Of course, and having function. Make sense? This is the famous formula Euler scheme, also called Euler's method, for the differential equations. Any questions? Okay. So let's apply this to population growth directly. It's so simple that we can afford doing this. Having forward Euler numerical scheme, here are equations. We can write special formula for population growth, by simply replacing f with RU. Because this was equation for population growth. Just our function was simply some constant r, and u as just the size of population in this case, And here is the formula that the size of the population at the time n plus 1 is equal to the size of population at times n plus dt, so time steps times r times again un. Or using original notion, we can get that, we just replace u with n. So n clearly states that this is the size of population. As usual, we prepare general solution. So this means that we would prefer to have, writing function that is ODE, like something like that. And it's good to point out that while Euler methods is useful, and it appears in many places, still often in practice more accurate and efficient methods are used. Everything has its uses, also Euler's method, but this is how it looks in practice. Questions, comments? Everything clear? Okay, perfect. Or I got lost to summary. Okay, no complaints. Okay. So finally, let's do some coding. So should I code it by hand? Maybe I will code it by hand. Let's try and code it by hand. So new folder. Okay, so script to solve population growth by using FE. Okay, as we can see, to generate this plot, we have n0 equal to 100. And we go from time 0 to 20. So the end equal to 20. And what else do we have? Okay, we have to assume some parameters. So it looks like dt is equal to 1. Okay, so we can solve it, of course, in many ways. So we can solve, we can generate lean space t end, so to have dt and t is equal to t end by dt, I believe, plus 1. Let's run this code and see if it gives us what we wanted. Exactly. And now we have to have placeholder for our solution. Yeah. So we're looking for n. Yeah. So n will be our population growth. Yeah. And so I will allocate space for it. So n equal to 0 size of t, because it will have the same size because we are looking for the solution on the time grid. So this is, I hope, pretty clear. Yeah. Then n of 1 uh, is equal to what? What is equal n of 1? What is the value of n of 1? Is it clear what I have written right now? So this, hmm? Yeah, n0, exactly. Because, okay, so this is our time mesh points, yeah? And those are, values of the population at time mesh points. And n is to be computed, of course. So the values of the n are to be computed, but we know the value f times 0, yeah, and we have to assign it because we will then be able to get all the rest of them. Yeah, perfect. So how to implement this scheme? Here in MATLAB? Oh, in general, yeah, you're right, yeah, but you are already thinking about the abstract. But here we have special case, yeah, and here we have this equation that is already just forward that march in time, yeah. So we have here value f at n plus 1 based on value at n. So we know that value at 1 is equal to n0 plus dtr n0. Yeah. And then we know that n2 is equal to n1 plus dtr n1. And so up to nt. Exactly, just a for loop. For I equal to what? This is one of the options. Of course, depending where do you put plus minus, but it can be from 2 to nt. Yeah. And here inside for loop, we write that n of I, yeah, because we start with 2 and we know the value at 1. And now we are just rewriting this equation. Yeah. So I is equal to n plus 1. That's why we start with 2. So it means that here we have n of I minus 1. Plus dtr and the same. Okay. So will it work? Fine. Yeah, so you clearly have some experience with programming. Exactly. Yeah, it won't work because we haven't defined R. No, No, I have no idea what is value here. I should write it on the slide. Let's say R is equal to 5, and we'll see if it works. Yeah, I think it's not super realistic. So, okay, let's make it. So let's see if it works. Yeah, it works. Nice. So it calculates n, and it's full of values. Okay, just 20 values. But yeah, it seems that it looks pretty okay. Yeah. Now we also have exact value to calculate. Yeah, so we can also calculate n exact. Does anyone remember what was the function? I think it was n. Yeah. Yeah. I think it was r times p. Yeah. So I think it should work without the dots. But yeah. Because here we have just calculations based with the numbers. Yeah. Okay, so it works. And now we have to make this kind of the plot. Okay. So plot Tn, and here I'm using some dots. Yeah. And T and exact. Yeah. So we can make let's make it somehow variable time in let's say weeks, whatever is the scale depending what kind of species we have. Yeah. Y label, it's what is on what is at Y label? Hmm? No, I don't know if you are talking about people. Yeah, I think that with people we have some other numbers, especially it's rather years than weeks. But yeah, population size, let's say. Yeah. And then we can add some legend to have it the same. And first entry is numerical using forward Euler, and second is exact. And now, great moment, let's run it. Yeah. So I think that we have to improve our grid. I think that the grid here is 0.5. And the growth rate is much smaller. I should have checked it. But okay. It's still too large. So yeah, maybe because it just skyrocketed. Okay, I think that the value that I was using is exactly 0.1. Yeah. So thanks. So after some checking, we have those values. As you have seen, for larger values, we didn't get exactly the solution. So then we have to tighten our grid mesh. Yeah. But here is just mostly to just show that, like in those cases, in general, this method works with reasonable grid. As you can see, the characteristic, yeah, so it works, which is nice. Yeah. Another characteristic is that as you can see, the error grows. Yeah. Because clearly here you have the small error, yeah, and then the error have tendency to grow. Yeah. What does it mean?
It's just exact.
What is how it's called this kind of phenomena in numerical methods when the error have tendency to accumulate and increase like here. It the same name like it's control. Yeah. So it diverges, that's true, but it has specific name. Yeah. For example, in a control, it's called that when you push it from the equilibrium, that it became the system. What happens when the error arises of the control? The system became unstable. Yeah. So it's stability. So this method is not stable. Yeah. So to ensure that the method is stable, or here it provides reasonable solutions, we need small time steps. Yeah. So yeah, it has tendency to become unstable. So but okay, it's not the most crucial term. But yeah, I just hope that you have heard about this. But okay, yeah. But it works in general. Yeah. Take a look that we use very coarse in this example time grid. Yeah. So of course, if you would here, I can switch to MATLAB. Here, if you use O, for example, 1, which is still reasonable because now we have just 40 elements, and now with 0.1 we get like 100, yeah. So nothing crazy. And as you can see, now it follows much more closer to this line, yeah. So in general, it works, yeah. And it's just a little matter of tuning, yeah, about the scale of the problem and the time mesh. Okay, and I can see that I also make here some quiz question. Okay, because I didn't read it, but yeah, this method has simple geometric interpretation. But yeah, okay, yeah. Let's see if you figure this out. What is the geometric interpretation of the forward Euler method for solving ODEs numerically? It approximates the solution curve by using tangent lines at each time step. It integrates the solution exactly over each time step. It approximates the solution by using second-order derivatives. It fits a polynomial to the solution at each time step. I hope it's not tricky. Let's see. Okay, no chat questions. Okay, yeah, exactly. It approximates the solution curve by using tangent lines at each time step. Second order derivatives, well, not here. It fits polynomial, yeah, but okay. So we get it right. Nice. So It also means that you can, in practice, even almost solve this by hand. It's so simple method. Yeah. So we'll give it a try very briefly because we'll use also this result. Yeah. And construct the solution for forward Euler method. Yeah. Just as a break. Yeah. So consider equation u prime equal to u to simplify the things. Yeah. So we have population growth equal to 1 with u0 equal to 1. Yeah. And time steps dt equal to 1. Okay. And we start with t equal to 0, and then we draw a line with the slope u0 equal to 1, and mark point at dt equal to dt. And we will repeat it to 3 steps. Yeah. And we will check, how the number goes. And yeah, and then I think that we will also write some tests based on this for our forward Euler method. Okay, so let's see if it will work. Yeah, so let's do this together. It worked last week, so I hope that it will work also today. Okay, yeah. So let's try to do this. Yeah. So of course we need what we need, a frame that we will put it. Yeah. So of course the frame is of the same type like the frame that we were using. So we have to start somewhere at some 0 point. Yeah. And then draw line in time. Yeah, we'll repeat this construction only for 3 time steps. Yeah, so let's put here 1, 2, and 3. So maybe it wasn't needed to be so wide, but okay. And of course, then and here we have the time in some measure, and it's not provided. So let's see that now we work with seconds. Yeah. We work with seconds, and our function u prime is simply equal to u. Yeah. So f of t, something is happening with it sometimes. F of t u is equal just u. This is clear, yeah. But okay, yeah. So and we know that u0 is equal to, I believe, 1. So here we have y-axis. And what is at this axis? Yeah, so u. Yeah, but population, exactly. So u. And it's just a number, yeah, so it doesn't have specific unit, yeah. And we'll start here at 1, yeah. Okay, hopefully it will be fine, yeah. So at the bottom, yeah, here at the bottom we have provided time grid, yeah, so this is defined. And now we have to find the solution according to geometric interpretation, yeah. So of course we have at 0, we have point here, yeah. So this is our u0. And so what I should do now, yeah, according to
Before. So u n plus 1 equals u n.
No. You are using algebra. Now we are using geometric interpretation. And so we are using that it approximates the solution by using tangent lines at each time step. Okay. So start at t0, draw line with slope u0, and mark point at t equal dt. So this is geometric interpretation. Yeah. because this formulation is algebraic formulation. It was also written here. I think that I haven't read it, but to progress the solution from t to tn plus 1, we draw a line from point of the solution at time n with this slope and mark it at the next slope. So that's why it mentioned about this tangent. Yeah. So what is the coefficient of this line? Yeah, exactly, it's 1 because u0 equal to 1. Yeah. So we draw a line. Yeah, you cannot see it. Yeah. So we draw a line. Yeah. With the slope. Yeah. With the slope 1. Yeah. Starting with this point. So it crosses at this point, okay, not starting, but crossing this point, t0 equal to 0 and u0 equal to 1. Yeah. And according to the formula, the next point is what is value? Exactly, it's 2. And because it crosses here at t equal to dt, so t equal 1. So here is the next solution, yeah. So here is our u1, yeah. So u1 is equal to 2, yeah. So to get the solution at next point, we have to draw a line with a slope equal to 2, yeah. It's kind of intuitive that the slope grows because, as you might remember, the exact solution is exponential, yeah. So we are expecting it to grow exponentially, yeah. So to get it, yeah, we can draw next line. So here is the line with the slope u1 equal to 2, yeah. So we have the line with this kind of the slope, and the line that is crossing the point t1 equal to 1 and u1 equal to 2. So here, yeah. And now we are looking, what is the crossing point? Crossing point between t equal to 2 and our new solution, yeah. So now we get u2 equal to 4, yeah. And now let's make this third step, yeah. So now we have to draw a line from the point that we just marked, yeah. So t equal to 2 and u equal to 4 with the slope equal to 4 because this is value of the function, yeah. Because all this translates that u0 prime equal to 1 and u1 prime equal to 2 and u2 prime equal to 4. Maybe I should mention it earlier because this u prime defined as what is the slope, not u, yeah. And here for simplicity, we just have u prime equal to u. That's why we draw a slope equal to that number, yeah. So now we have to draw another line with a slope equal to 4 and equal to u2 prime, yeah. And now having this, we can calculate u3, yeah. So u3 is equal to 8. Easy? Understandable? Yeah, nothing fancy. Fortunately, yeah. After getting how it works with one point, it's easy to get for the others. Yeah, and we will stop here because those slopes start to be pretty steep. Yeah. So, and I think that already the next point will get out of the reach of this screen. Yeah. Uh, And of course, we can just calculate it by hand. Yeah, it's so simple example. Yeah, because dt is equal to 1. I have to change the ending of this writing pen. And we know that u0 equal to 1. Yeah, and we know that u prime is equal to u. So again, the finish of the problem. So we can calculate it numerically, but for those 3 points, we can calculate it as well by hand. Okay, redefinition of the problem. Yeah, we can calculate this again by hand. So u1 will be equal to u0 plus dt times u prime 0, which is 1 plus 1 equal to 2. Yeah, and this is equal as well to u prime 1. Yeah, because of the definition of our because of our function. So u2 is of course equal to u1 plus dt u1 prime, which is 2 by 2, 2 plus 2 because dt is 1. All the rest is 2, so it's 4. So this is also u2 prime. And u3 is of course u2 plus dt u2 prime, which is equal to 4 plus 4. Equal to 8. Yeah, so of course all this works and matches. Any questions? Perfect. So we have another quiz question. What is the value of u at t equal to 3? Looking for the rate of the answer, it seems that I put some of you to sleep almost.
How much do you need again?
Hmm?
How many people are watching this again?
Yeah, 21. Okay, yeah, quite well divided. Yeah, that is the share that this has absolutely no sense. It's not so high, so I'm not very worried. Okay, so this is the next question. Sorry, but yeah, switching between those windows and all the system, it gets complicated. But okay, forward Euler general case. Yeah. So again, we need a program to solve a whole class of the problems in this form. And the forward Euler scheme is just like that. Yeah. And let's see the general implementation of the ODE. Yeah. I think that I save it on my MATLAB online. Yeah, so let's just give me a second and I will log in and download it from there. Yeah. We mostly uses this MATLAB not online. The switching between windows sometimes, doesn't seems to work at all. Now, okay, it's here. Yeah. Okay, is font readable to all of you? Or should I increase it even more? Okay, it's fine. Great. So, so here is just this one of the possibilities to implement forward Euler, yeah, as a general function. Yeah, there are many, uh, but okay. Uh, in this interpretation, yeah, we have three input variables. Yeah, what is f? Exactly. So it's some kind of function handle that define as function with taking t and u. Does it take t and u? It's here. Yeah, it takes t and u. Yeah, as you can see here, because in some implementations I have seen that it takes u and t. So yeah, but here we follow. I think that it follows standard MATLAB notation. Yeah, we can check if it hasn't changed because it also has tendency to change. T-span. So this is the second argument, and here T-span, maybe the name is not the best because it tells about dt and t end. Yeah. So it is assumed that this vector of so I will change the name because yeah, span sounds like it spans something. Yeah. So it provides dt and tn. Yeah. And u0 is u0. So it's value of the solution at time equal to 0. So we get the dt and t from here. Then we get the points. Yeah, I added +1 in this. It depends where you put +1. But +1 is put here. Yeah. So okay. So we firstly define u as zeros of size nt+1 and length of u0. Why this is the case? Because this implementation assumes that u can be a vector function. Yeah. And why we can, of course, for population growth, this is only single value. So it will be zeros of this one and one. Yeah, no problem. But for example, already in the case of like mass spring damper, we will already have to define two functions. Yeah. Yeah. And two initial conditions. Because then we get, so it's useful to write this that it can support vectors. T is the output vector with time, and we calculate it here. Yeah, so 0 to nt plus that t. F with length of u. Then we assign u at the first point. Okay, and then implement the loop that marching time. So standard interpretation. Un plus 1 is equal to un plus dt times function at times n. Okay? Make sense? Any questions?
This is a cat sign.
Yeah. Yeah. Create a demo to solve population growth problem. Okay, so we will solve this population growth problem. Yeah, using our function. Yeah, So I just copy the original. Rename it. And we will remove all this looping for the call to Tn is equal to ODE FE. And we have those parameters. So we have f. So f is a function that we describe t and u. Okay. And in our case, it returns the expression for population growth, which is r times u, as we have in slides. Yeah. T info in our case is dt t end, and u0 is n0. Make sense? So we can remove this, and this. Yeah. So this is also the readability of the code improves. Yeah. So as you can see here, we have just definition of the problem. So starting population size, what is the growth rate? What is the end time? What is dt? So originally it was 0.5. So let's start with 0.5. Then we just call the function that hopefully works. And exact, yeah, the same, and then we make a plot. Make sense? Let's run it, and yeah. And to be sure, let's maybe clear our workspace and run it again. Yeah, of course. There is no reason for it not to work. Of course, there can be some errors in this ODFE, yeah, but yeah, as you can see, it's not really here. Okay, so now let's do a simple hands-on. Yeah, so test script for forward Euler. Yeah. So I will put forward Euler to Moodle so that you have access to it with no Here is our force. Now we are in the topic 4. Okay, so here is our file. Why? Okay. Okay. Now it should be there. Yeah. Yeah, exactly. So you can find ODFA tool at Moodle. Yeah. And now the task is to create script test ODFF.am, yeah, .m. And make section in test file that calls all the FE to compute 3 times steps in the problem u equal to u with u prime equal to u with u0 equal to 1. As you might remember, the solutions were just 2, 4, and 8, yeah, and check if those values are exactly the same as obtained earlier. And then we have another, information here that the problem u prime equal to RU, which is just the problem for the population growth, has closed form solution for the forward Euler method. Yeah, and here is just equation provided for it. So u an, yeah, this is closed form solution for forward Euler approximation of this solution. So after calling forward Euler for arbitrary R and U0, yeah, you just should get those numbers up to numerical precision. Yeah. So use these results to construct second test that runs several steps in ODE and compares the computed solution with the listed formula for UN. Okay, is it understandable? What is the task here? Do you have any questions? Any doubts? Do you know how to proceed? Okay, let's take a few minutes and try to solve this. there anyone who knows how to solve this? Yes, that's. Anyone knows how to solve it? Do you want to see solution? Okay, yeah. Okay, it seems that this task causes some challenges here. So let's create the script as it's written here. Okay, so create a script with all the tests. Okay, so this step done. Make a section in test file that calls ODE to compute 3 time steps in the problem u prime equal to u. Okay, so I copy paste the text of the problem and makes a section. We make a section test file to call ODE to compute 3 time steps in the problem u prime. Okay, so it's a little too complicated. U prime equal to u with u0 equal to 1. Yeah. And compared to the 3 values, u1, u2, and 3 obtain error. Yeah. So how to start this? Yeah. Yeah, we can. Yeah. So we know, like it's written here, let's code everything. Yeah. To compute 3 time steps. Yeah. So 3 time steps, we have this t info. So 1, 3 should do the trick. Yeah. So to make it more clear, yeah, we can write the time step is equal to 1 and time is equal to 3. Yeah. And then t info that we will pass is time step and time. Okay. So this is the coding to compute 3 time steps. Yeah. Make sense? Okay. Next information. The problem u prime equal to u. How to write this? How to write this? How to code this part? The problem itself. So let's back maybe 2 slides. Yeah. Here. Here is the way that we define the problems for our general case. Yeah. So what does it mean to define the problem? Define the problem. General problem consists of 2 elements. Yeah. So one element is what? What are 2 elements here? Or even 3. Here you can see all the 3 elements that came into kind of into the function. And this is, of course, arguments of the ODFA function itself. Yeah. So what is the first argument? F is the first argument in ODFA. And what is F? Yeah, function of TU that defines the problem, how the problem looks like. Yeah. So how to code this in this way? That our F is what? It's written here. It's equal to U. Yeah? It's written here, yeah? U prime, which is our function of t and u, is equal to u. This is this kind of abstraction that we have to deal with, yeah? So function that represents derivative is u. This is written here. Yeah. You mean why f is function of tu?
Not just t. Why is function of t? You don't have the.
No, f is function of t and u. Yeah. And and the reason why you have t here, despite our function is not the function explicit function of time, is because we want to solve. We have written program for generic problems, and generic problems depends on time. It happens that our program doesn't depend on time. Yeah, so we just ignore this t. Yeah, but here we just have written it in general form. So we also implement this in general form, and there's many problems that depends on time. Like we can, if we will see this, for example, or yeah, in one way or another. Yeah, it's enough that, for example, we have more realistic problem where this growth rate R is not constant but depends on time or depends on resource or something like that. Yeah, but here because we don't have explicitly time, so we simply don't use it. Yeah, and we keep it because this is the interface. Because function, it's the interface. Yeah, so the interface, it means that our ODE function that was coded based on this requires that the function f that defines derivative takes two arguments, t and u. Make sense? Clear? Okay, perfect. So this is how we define the problem. Next part is to write. So compute 3 times steps. Yeah. So it's here. Now we have u of 0 equal to 1. So how to write it? Exactly. And compare to the three values. Yeah. So u expected is equal to 2, 4, 8. Something strange. Okay, because it uses some Unicode. That's why it displays in some strange way, but okay. Okay, we can write it in many ways. I just decided to write this as a vector. Is it okay that way? Okay. Or do you want to write u1 expected, u2 expected to be more explicit? Hmm? Okay, there is no comments. Okay, so here we, I think, get everything from this description. Yeah, so we just write all this description into the code. Yeah, and now, run the test. It's the next part. Yeah, and then the last part will be what? Check the results. Okay. So running the test, it means that we have T U computed is ODE FE, and then F is F, T info is T info, and U0 is U0. No, that, yeah. Damn. Okay. So now we run the test. So we call the function, and we have to check the results. Yeah. So what was the function that was used to check the results? Yeah, it was assert. And what we are expecting to have? So first of all, not. Because we can write it that way, yeah, but then we have to put here u0. Okay? Hmm?
Array, you just compare you expected it to.
So what was the
You just compare you expected equals, you compute that it would be an array of Boolean.
Yeah, there are many issues with this. So
Can use the function.
maybe. Yeah, let's try. Hmm. Or something like that, yeah. And simply we can run it to see if there is nothing happens, yeah. I'm not sure I wouldn't write it that way, yeah. So values from OD, yeah. So it doesn't work. There can be many issues for this. So one of, yeah. So one is that they have different sizes.
The same problem is that the computed is transposed.
Yeah. So we can just make them the same. The same. We can just vectorize them both. So let's see if this will work. Okay, this works. I don't like this solution, of course, because we are now checking if the values are equal. Yeah, but I think that it's acceptable because we get exact values. Yeah, so we can check if it's equal. Yeah, normally I would calculate the norm of difference and check if it's more than tolerance because we don't care about round-off errors. Here we have equal numbers, so it works pretty well. So it works, so let's leave it. Okay. Any comments? Any questions? Everything is clear? Every step I take? Okay, because good, because we have still the second one. I hope that this will be even simpler because now, so here it wrote, yeah, make section. So we want to have multiple problems, so we'll divide them into sections. Yeah. So let's make this test. Yeah. So problem u prime equal to RU has closed form solution. Yeah. So again, how to write problem u prime equal to RU? No, this font doesn't seem to work. So u prime equal to RU. How to write this?
R times U.
Yeah, and of course it won't work because R must be defined. Whatever, 1.2. Okay. Has a closed form solution for the forward Euler method. Yeah, so here we have the closed form solution for the forward Euler method. Yeah. And we have to somehow put this into writing. So U0, so we need U0. Yeah. It's another way, if we don't know, I just put it in number random value, because it must work for any U0. The R is defined, dt. What is dt? What to put as dt? Okay, we put dt. And then we need also t end. Yeah, so we can define that we have okay. So we can calculate that u expected is equal to, we need n. I think that n will be, it's a good question if it starts from 0. It should start from 0, yeah? From 0 to 53. If the size won't match, we'll check it. So it's u0 times 1 plus r times dt and to power of n. Okay. So this is one of the ways to write it. Does it look correct? And does it look correct or not? Any questions? Why? Why I start this with 0? What?
Should start from 0, so you can get like accurate things, and also because Euler forward is probably better at like U0 than starting later.
Yeah, but it's I think that it's nowhere written that it start with 0, yeah? But it's clear that it's 0, but because here we have power, and to get at u0 equal to 0, yeah, we have to have this to the power of 0, which equals 1 always. Okay. And now we can get a numerical solution. F is our function. The info is dt and time. And u0. And we can check the results. Yeah, let's see if it will work. How do you think it will work, this test? Okay, it doesn't work. The number of elements is correct. But I believe that the issue is that the norm of U computed yeah, exactly. It's not numerical 0. It's not 0. I mean, it's close to 0, but it's not 0. So here we have to rather calculate error. We have to calculate the tolerance. And hope that this will be enough. And now let's run it. Okay, so it still complains that the error is two times the, okay, so tolerance is too strict. It seems that this problem is not so well defined. Okay. I'm even surprised that this error is so large, but we have no time to analyze it because it's not super large, but it's still pretty large. Yeah. So yeah, it has tendency to rise. But okay. Can you see an error here?
Um,
Because those are vectors. So ABS would just still return your error. Yeah. So you have to figure out some kind of the norm. So ABS was good as a norm for scalars. Yeah. Because it's one of the norms for scalars, but when you have vectors, you have to use one of the norms. Yeah. So here we just use the built-in function norm because we have to get just one scalar value to compare against. That is here. So this is pretty typical way. Yeah. If you use ABS, then you have to use ABS max. That max value from those ABS values of the differences. Yeah. This is another option, and I think this is norm 1 simply. And here by default we use norm 2. Understandable? Yeah. Okay, I'm a little worried about this, why it rises so large. But okay. Yeah. Let's say that it's not the most crucial at the moment to analyze this part. But about the implementation, this is how the implementation would look like. Any comments? Questions? Is it clear why all this looks the way it looks? Okay, perfect. Yeah. So someone there. We have just yeah. So now we'll get a little into vibrations. I believe that we will end up this topic next week. So yeah, everything in life is vibration. Yeah. This is one of the representation of the vibration. Water under sinusoidal vibration of 11 hertz. Yeah, I take it from Wikimedia. And of course, for us, we are working with the most basic vibrational systems, which is an oscillating 1D system. Yeah, so this is the prototypical mechanical system. Yeah. The most fundamental model in dynamics. Yeah, surprisingly, a lot of phenomena can be described by this simple model. Yeah? And if we start including some nonlinearities, then there are even more. Numerous materials act like springs. Yeah, we will start with the undamped system. Yeah, so we will assume that this damping that it's shown here, C is equal to 0. Yeah, so we have just M and K. Yeah, and the simplest meaningful model of free vibrations has this form. Yeah, that displacements. Okay, it should be U. Displacements, acceleration in time. Yeah, plus omega 0 displacement in time is equal to 0. Yeah, I think that pretty well-known model where omega 0 is given parameter, natural frequency of the system. We need two initial conditions, so we need to know both position and velocity to solve the problem, because here we have second derivative. And we use here Newton's notation with dots instead of Lagrange notations with those, I don't know, comma, whatever, to denote time derivative. Okay, which is also typical for physics. No. And some simple quiz question related to this. In the context of oscillating quantity system shown on the slide, which equation represents the simplest model of free vibrations, and what does omega 0 represent? Okay, let's see. Yeah, good. Yeah, how the last one always gets quite nice attention. Okay, derivation of the 1D model. Just a reminder. Differential equations allow us to understand, predict, and control the oscillations. Nice. Yeah. Assuming that the model works reasonably well with respect to reality, which is often the case, fortunately. The simple model is mass attached to a spring that moves without friction. Many systems can be reduced to this model. Perfect. Newton's second law of motion gives us inertia force, so gives us information that that in general we have the inertia force that equals to mass times acceleration, which is mx double dot in the context of this figure, yeah. And the spring force pulls or push, yeah, the body back and back and forth, I think it should be, against displacements F equal to minus kx. So we have this type of equation, yeah, and after putting it on the one side and transforming with omega 0 equal to square root of k over m, yeah, we get this equation. Yeah, nothing tricky here. And this is the second order differential equation that needs two initial conditions. So we have to know what is the initial position of our system and what is its initial velocity. So let us assume body at rest with initial displacement. Yeah, so it means that we have the model. Yeah, and in we assume that x is equal to 0 when the system is in equilibrium. Yeah. So then we just push it little, against the spring in one direction of another. And of course, if we release it, yeah, with zero velocity at the start, because of this, in some of the initial displacement, the systems will start to oscillate. Yeah. So as we can guess, because the system will oscillate, we'll get some the solution of this. At least it looks plausible, yeah, because it's sinusoidal, one of the sinusoidal functions, yeah. So it will clearly oscillate, and natural frequency, as the name suggests, yeah, is the frequency of the oscillation. X0 will be amplitude, yeah, because there is no extra energy to the system, so the system cannot go further than this X0. And we have no friction, so there is no damping. So it will just oscillate indefinitely. Clear, yeah. So, but it also means that we have definition of the problem, yeah, and with some exact solution that we can compare against, based from the perspective of our implementation, yeah. And just one example of equivalent system, yeah, that can be represent some real case scenario, yeah. So that if we have this kind of just pendulum, yeah, so on the string, large mass, yeah, and we assume that we are oscillating, yeah, with around the equilibrium, and of course equilibrium is the position of the pendulum when it's just vertical, yeah. And assuming that we have small angles, yeah, because then this allows us to linearize the model, yeah, just like here, yeah, that if we have small oscillations, let's say that up to 6 degrees at the start, yeah, that we can assume that sine on theta is equal to theta, yeah, with very good approximation, that you can transform this this formulation into the same equivalent system. Yeah. So this kind of oscillating system that oscillates, yeah, the swing of the pendulum under assumption of small oscillations. Yeah. So with small this angle theta just behaves exactly the same like mass spring damper. Just definition of the omega is equivalent, slightly different. Yeah, and here, of course, we can calculate the period, but we can also calculate the period of oscillations for standard mass spring damper system having omega 0. Make sense? Yeah, nothing super tricky here. I can see that I also will make a question out for this one. Which I hope it's also reasonably simple. It has two Qs. So by the way, do you consider challenging the things that we are doing here? Hmm? Yeah, okay. Good trade-off. Reasonable answers. Okay, and here is pretty important step, how to obtain numerical solutions. Yeah. So do you know how to, in general, how to reduce the system, second order system to first order system of equations? So it's all about this, yeah? So now, can we solve second order derivatives using forward Euler method? Yeah. Yes, we can. We can use, it's called a trick, to write second order equations to two first order ones. And this is very important, yeah. There are methods that can be applied directly to second order equations, but they are not so common, yeah. For example, Newmark's method, HHT, yeah. So there are this kind of the methods. But in the most standard methods for solving ODEs are written in the way that they solve first order equations. Yeah. So we have to reduce second order equations into first order equations. And it's simply done by introducing extra variable. Yeah. So we are introducing extra variable for the velocity. Yeah. And then we can rewrite this equation in the first order form. Yeah, so then we have just, let's say, two variables. Maybe it's a little bit more, but we have u and v instead of x and x prime. Yeah, so u is just x and v is just u prime, which translates to x prime. Yeah, and after putting those two values, okay, yeah, so this is just displacement. This is velocity of the system. Yeah. But putting them here, we have that v dot plus omega 0 u is equal to 0. Yeah. So clearly first order system. And then we have to also include the information about this transformation. So we end up with this kind of the system. Is it clear how this is obtained? Or almost clear? Okay, it's pretty important. So so in general, we want to solve u prime equal to f tu. Yeah. So this is our description. Yeah. And now we have the problem that it's written as x double dot plus omega 0, I think it's yeah, exactly squared, equal to 0. Yeah. So clear we have second order equation and we need only first order equations. Yeah. So not to mix notation, let's put it y and y. Yeah. Okay. Again, the same. So now we are using new equations that are expressing the first order form. So u is equal to x. I have to replace it, sorry. And v is equal to x prime is equal to u prime. And this is velocity, yeah. And now, of course, we have that x double dot is equal to u double dot, but it's also equal to v dot. Yeah. So with those two variables, u and v, yeah. So yeah, instead of having just single variable x, we are introducing two new ones, u and v. Yeah. So it also means that y is equal to u and v. Yeah. So we have to do, yeah. Is it clear why we are doing this? because we have to reduce the order. So we have to have variables that allow us to express the equation that we have here, yeah, the original equation, in the first order form. Yeah. So having those two new variables from here, we can write this equation, yeah, as v dot plus omega square u equals 0. Yeah. So, make sense? Yeah. So now we have to, so this is how it looks like, yeah. But what we need to get y prime equal to f, yeah. So what is f here and what is y prime, yeah? So y prime is by definition u dot v dot. Okay. So what is u prime? Hmm? Yeah, but based on the inputs, yeah. We need to, we need to base this information on the inputs. Yeah, exactly. It's b. Yeah, of course, you're right that it's x prime, but it's not of use here because, this is our inputs. Okay. Yeah. So this is the trick. And what is v prime? Yeah, it comes from here. Yeah. So it's minus omega 0 square u. Okay. So by combining those two information, yeah, we have that y prime will be p and minus omega 0 squared u. Yeah. And also then we have u0, y0, it's this extra information, which is u0, v0. So here we clearly see that we have to provide initial position and initial velocity to solve the system. And after reduction, we can write f as returning this vector. This is y, and y is f, y prime. Y prime define f, yeah? So this is we will return this vector. Yeah. So the last step is to write f as ty. So look, using kind of mixed notation. Yeah. So we will have what is in this input, what is v. So here we have function, yeah, because we know that y prime is equal to that one, yeah. So, but we don't have here v or u, at least here on the list, yeah. Hmm? Yeah, y2, yeah, exactly. So using MATLAB notation, it's y2 because this is v based on information here, yeah. So how looks the second row? Exactly. Is it clear? And this is the transformation that you have to be familiar with, because yeah, because this is the way how you can express this kind of equation with the form that can be solved by MATLAB. Yeah. Is it clear? All the steps? Okay. Yeah, that's good. Yeah. So because one thing is, again, how do we write it? Because of course this is mathematical description. Yeah, but then we have to translate it into MATLAB language. Yeah, of course this is constant, so we'll define it somehow. Yeah, but we have to, put this information in proper format. Yeah, and the format is about y vector. Yeah, so we have to define y vector, y0, and y prime. And y prime is defined by a function that takes t and y. Okay. And we just, run out of time, or not necessarily run out of time, but we get to the end of today's lecture. Yeah, because we still have one running assignment. So I won't give you any extra one, yeah, for the next week. So the next week we'll end up with those ODs, yeah, and then you will get some assignment. Yeah, let's see how it will look like. Yeah, I will check it. Either it will get a small part from numerical integration and then the small part from OD, or it will be just purely about OD because we get into this topic. We'll hopefully start talking about nonlinear equations, or I will shorten the topic and start and end about nonlinear equations. And in 2 weeks, will came Alexander and discuss with you solution of PDEs. So partial differential equations and their applications to, for example, finite element method. How to discretize, them. Okay. Any questions, comments, complaints, suggestions? If not, then thank you. Yeah. And we'll see you next week. So thank you, everyone. Bye-bye.
Bye, and thanks.